All right. So, good afternoon to you all. You are welcome to the week 4 of our IoT hardware training with the DIPPER lab. So, for those of you who were with us last week, we started with schematic design. We agreed on a project to work on. We said we want to do a water monitoring system, right? And so we started with the schematics. So let me open a schematic right here and let me first share my screen. All right. So I'm sharing my screen. This is what we did so far. Last week, we said we are going to use the ESP32 Room 32E because it's a very common chip. Sorry, a very common module. It's used on some development boards. You can buy them online and use them in your projects. So now we want to continue with what we were going to do. Let me quickly brush through what we've done so far. So this is the ESP32 chip. It's got some pins that we are going to connect to enable the work. There's 5 volts. Sorry, there's VDD here, which must be 3.3 volts. We read that in the data sheet. It should be around 3 to 3.6, and we saw that 3.3 is a very common voltage level. So let's use 3.3, and here's our ground connection. These are flags that we are using, and they help us to keep our schematics clean so that wherever the source of our power is from, we don't have to route all over the page, but we'll just use these flags. They are like variables, right? Right here is a jumper. So we read in the data sheet that in order to select the startup mode for the ESP32 chip, right, you need to use a jumper between IO0 and ground. If this is not connected to ground, the ESP32 starts up normally where it's executing whatever code you have uploaded to it. And when the jumper is shorted, could you please pause for me? Hello. Hello. All right, sorry for the interruption. I attend to an urgent call. Okay, so I was back at IO0. I was describing its function as the boot selector for the ESP32, where when it's not shorted to ground, the ESP32 when powered up starts executing whatever code you have uploaded to it. And when you short it to ground with this jumper, uh, the ESP32 enters flashing mode where you can upload, or the technical term, flash. So when you can flash new code to your ESP32. Okay, so this is one of the requirements there. Without it, we are going to run into problems. Then we have TXDO, RXDO. These are UART pins. Okay, UART is a digital communication protocol. I'm sure some of you have come across it. I recommend you watch videos on it to read something on it to know the basics of it. Alright, not too detailed. Martin Avoga, your hand is up.
Yeah, I wanted to ask, like the UART and the RX, are they on like On the ESP32, it says RX is on a different point and TX is on a different point, but you have them. Is it a thing with the chip, or is just like,
Are you speaking of
are
my
you an
schematic? Oh yeah,
what? Are you
do you hello?
Yeah, I'm here. I'm listening to you.
Do you mean that this is here, this TX or the
And
RX?
yeah, yeah,
Yeah,
like the label on the chip says TX is up and RX is down, but you have TX on IO2. So I'm a bit confused. That's all.
yeah. Sorry for the confusion. So this is an error. To be honest, this is a mistake on my part. This is supposed to be here because TXDO is IO1 and then RXDO is IO3, and I moved it here. So thank you for drawing my mind to it. It's a mistake. It's a mistake. Um, so one thing we should always do is that when we are done with our schematics, we have to go through it. And if you are working with a team, whether with a team or not, try and get someone to review the schematics for you. Martin, as I hope I've cleared up the confusion.
Yes, yes, you have.
Yeah, thank you very much. The last time too, I ended up connecting EN to sensor VP here. Okay, all right. I still make mistakes. We all make mistakes. One of my PCBs that I designed, I made a mistake, but then it was too late because I had already ordered it. So yeah, with these kinds of skills, with these kinds of projects, mistakes you make are costly. So let's move on. So I was talking about TXDO and RXDO. They are the two pins used in UART communication. TX is for transmitting serial data out of the ESP32 to a target, and the RX is for receiving data from the target to the ESP32. So one line for sending out data, another line for receiving data. If you take a look at other communication protocols, something like I squared C, it also uses two lines, but then one of the lines called the SDA is used to transfer data to and through. All right, so that's something important that you should look through. Okay, and the third one we had hooked up, that's the VDD. We used filtering a filtering capacitor and a decoupling capacitor. The decoupling capacitor acts as a temporary storage for power in case there are any fluctuations at the power supply where there's a sharp voltage dip or rise. It tries its best to keep 3.3 volts at the supply of the ESP32. And for the filtering capacitor, what it does is that it filters out high frequency noise in the power supply. All right. And lastly, the enable pin. This connection is divided up into two segments. Here is the reset section consisting of this capacitor and this jumper. And then we have let's call it the enable section. Actually, it's the enable section over here, which, sorry, the RC filter circuit, which consists of a resistor and a capacitor. So briefly, the RC filter circuit, what it does is that it slows down the transition of voltage from 0 to 3.3 volts at the EN pin. I give the illustration that when you are powering something up, there's theoretically an immediate spike from 0 to the voltage you are applying. So if it's 3.3, there's an immediate spike, but we don't want that. We want it to be a gradual increase, still fast, but a gradual increase, like maybe 1 millisecond. In 1 millisecond, it should have increased from 0 to 3.3 volts, and that is what this RC filter circuit does. Why the why the datasheet recommends it, I am not entirely sure. but I think it helps with stabilizing the ESP32, especially this capacitor. Because possibly if there are voltage transients where there's an immediate dip in voltage, the ESP32 would go off. If EN, if the voltage at EN drops below a specified voltage in the data sheet, the ESP32 would go off. But this network here could help filter out those transients and make sure that the ESP32 going off is because there was a cutoff, like an actual cutoff supply. Then we have this reset circuit here consisting of a capacitor and a jumper. So this jumper is going to short EN to ground when bridged, and that would mean that we are turning our ESP32 off, right? This capacitor is just for filtering at the um, the jumper, right? Something about parasitics and the hardware. It's recommended. The specifics, the detailed explanation, I don't really know, I can't give, but whenever you are using a jumper or a button, it's recommended to add a filter capacitor. All right, so this is used to reset the ESP32. This was supposed to be a button. So imagine the button is there, you press it and release it, and it's like turning lights on and off quickly. So that's the reset circuits for the ESP32. And we have a 4-pin connector here for UART. The two ends are for power, and the two inner pins are for the communication to the RxDU and TxDU. And lastly, we've got power flags. What the power flags are doing is that they are saying that 3.3 volts and ground are power inputs. Without these, we will get an error in our DRC because the ESP32 expects power flowing here. But then, because we just use a symbol, which on its own is not a power source like a voltage regulator, we are going to get errors, right? So when we bring in our voltage regulator or a battery or whatever source, we can take out these flags. Else keeping them there after we've brought in our sources will cause us an error, right? So that is what we did last week. Now let's continue with what we are supposed to do. So last week we said that we are going to use some sensors with our ESP32 to monitor water and upload the data to upload the data, right? Okay. So one of the sensors that we said we are going to use is the BDT sensor. That's right here. The next sensor we said we would use is the turbidity sensor is used to measure the clarity, the dirtiness of water. Okay, so it works on the principle of light emitted and received. One of the heads emits light, the other receives light. If your water is dirty, the receiving end will receive less of the light produced. If it's clear, it's going to receive almost all of the light produced, all right? So that's just the top level principle of the operation of that sensor. And we said an ultrasonic sensor. So for the ultrasonic sensors, we have this kind, which actually measures distance. The ultrasonic sensors measure distance, but we can use it to measure water level. And we have the waterproof version. So we said which one to use, right? Well, I think we can use both of them. We can use both of them because they have the same pinout. This one has VCC. If you zoom in, it has VCC, trig pin, echo pin, and ground. Same for this one. Well, we can't see. Okay, it's right here. Same thing here. VCC, which is 5 volts, trig, echo, ground. Yeah, so trig is always before echo. So whichever one you end up using, if you are going to work on this project as a personal project, whichever one you end up using, we can do a connection for it and both of them will work, all right? So we are going to provide a 4-pin connector for this one. For the turbidity sensor, we are going to provide a 3-pin sensor, a 3-pin connector because so this is one worrisome thing about online stores. So this sensor doesn't have its parameters specified. So I have a turbidity sensor here. It's the the labels are written on the board. So let me quickly check it out. Over here, it's just one picture, so we don't really know. So let me quickly check it out. I'll join you. Okay, so I am back and I have confirmed the pin out. So looking at this image, starting from the top is ground. The middle is the analog out and the bottom is VCC. And this sensor too requires 5 volts. It requires 5 volts. That too is not stated here. But if you look for the BDT sensors work on the same principles. If you want to use a sensor, your best bet is to search online for people who have uh, done a blog like this to show how to use it. Right, so over here, when you finally connected it up, you would want to go through this to see how to program it. We can see over here that 5 volts is required, 5 volts is used. Yep, so this is a 5 volt sensor. Okay, I think there was one more, there was one more that said we are going to, yep, is there one more? Let me see. Let me quickly check something. Okay, so this one, I'll have to take note of it and we would come back to it We just wanted to make sure this exists before we continue. And it actually exists, so we can continue. But quickly, let me check something again. Okay, all right. Yeah, yeah. So that was just by the way. Okay, so the one more device that we are going to add is the pump. The It could be any of them. There is this one. If you use this one too, it would work. But then you would see in a moment why any of them should be okay. Okay, so let's get to the connections, right? So first things first, our turbidity sensor module, our 5 volt turbidity sensor module. Okay, so if you look at how the module is, right? This is the module. You can see that there is a PCB with connections or connectors on it. Okay, and we want to integrate this into our PCB. So how exactly are we going to do it? Well, one simple easy way is that you'd you'd create uh, what's the word again? Female headers. So you would use these kinds of headers. They are called female headers, and they receive the male headers. So on the stability sensor module, there are some 3 male headers here. We use this on our PCB, and you can just slip. We use 3 of them, 3 female headers on our PCB, and you can just slip the you can slip the turbidity sensor module into them. Okay, another method you could try is that you could use the male headers. You could use the male headers or even these ones. You could use these very ones and solder them inside. All right, because they're already bent, I wouldn't prefer this method. I would rather first solder these on my PCB. Then if this comes unsoldered, I would put this on the PCB and solder that there, else I would unsolder these heads and put them there. But the basic thing is that it's very flexible. Um because every all the sorry because almost all the headers, the male and the female, they have the same pitch. The pitch is just the pitch is the spacing between the header pins. All right, so looking at this image, a common pitch value is 2.54. most of the headers on Oku Electronics are 2.54 pitched. All right, so the separation between the headers is 2.54. Same for male and female. So when the PCB is made, you can either fit in male, you can fit in female. It doesn't really matter. It depends on you. The important thing is that the space and the pitch, the holes that are drilled into the PCB are the same. Okay. So really we wouldn't worry ourselves on that. We will just put a connector there. And the connectors, when you are doing the routing, they will just appear as holes. They will simply appear as holes. Whether you solder in male or female doesn't really matter. Okay. So I'll just go with the male headers. I'll duplicate this and I'll put this here. Now our PCB requires 3.3 volts and 5 volts. Sorry, the module I mean. I'll just change this to 5 volts. I said that you should go to the power symbols last week. Go here and look for the 5 volts. But as I said, these are just variables, all right? So it's the same as copying 3.3 volts and then coming here to change it to 5 volts. It's literally the same. It's not the same as plus 5 volts because there's no plus here. So I'll just delete it. The plus is, I think, important. So make sure you add that. And we would also provide ground. Okay. Yeah, I was supposed to use a 3-pin connector. So we'd use this for the ultrasonic. We'd use this for the ultrasonic rather. We have to bring in a 3-pin. Yeah. This is what we are supposed to use for the yeah. So as you are doing your connections too, you want to make sure you place things correctly. Make sure they are well done, like in that sense. Engineering is not just about the calculations and stuff. You should also make sure things are done aesthetically pleasing, such that when we are done with our schematic and you want to give this to someone to troubleshoot or go through it for you, it's not a stress or it's not a stress for them to go through your schematic because you've arranged things beautifully and they can easily find what they are looking for. All right, so it's good to start from the onset. Your first project, try your best to make sure things are well pleased. And, so I'll call this tab and connect this here. Okay, so I just have to worry about this later. What was the pinout for the ultrasonics again? 5 volts trig echo ground. Okay, trig echo ground. Trig and echo. Hook those up to. Yeah. A bonus here. Let's take a look at our electrical roof checker. Run ERC. We get 4 errors. What do the errors say? It says that label not connected to anything. What are they saying? They are saying that we have created this label, connected the wire, but this is going nowhere. Like, it's like you just drawn a wire from the connector and then you've stopped. You've done something like this, right? So that's an error. So we have to come and connect this up to the ESP32 wherever we are connecting it, right? So that's just something interesting to know. And it's warning us about the 5 volts too, saying that it's not driven. All right, so we are not done. We don't have to worry. Click delete all markers to clear the markers. That the markers appear here. If you click close, they are still there, and it could be annoying. So just delete all the markers and close it. Okay, so we have done these ones, and I think we can continue. But for anyone who has a question, I would pause here to take any questions. Please, if you have a question within, let me say, 30 seconds or 1 minute, please ask your question. I'll take this time to drink.
Nat, please, for the error that you got, if you go ahead and then you open your PCB editor, can you do it? Like, would it work, or would you have to clear the errors first?
Yeah, hello, who asked the question?
I asked the question.
Aram, right? Yeah, I heard the
Yeah,
question.
yeah.
I just wanted to verify who asked the question. So you
Okay.
said if we were to leave the error there, the symbol not connected error, and we went on to PCB design, will we be able to route? Short answer, I
Yeah.
think, is no. Though I've not tried that. Though I've not tried that. Um, because on your schematic, this pin 2 is connected nowhere to the ESP32. Though we have not reached a PCB stage, um, if we go to the PCB2, we are not going to see anything there. So I have it opened here. We are not going to see anything here. Reason that we see nothing here is that we haven't clicked update PCB from schematic. Okay, so let's say you are done with your schematic, you save it, Control S to save. Control S to save. The asterisk at the top here has left. Go to your PCB, click update PCB from schematic, and we get some more errors. Most of them saying that cannot add C1, no footprints assigned, no footprints assigned. Still click update PCB and close. One of the footprints is added because that one is already specified. Okay, so when we are done with the schematic, another thing we have to do is that we have to select the footprints. The footprints basically are what is actually routed on the PCB. So when I showed you the CNC PCB we did the last time, how it looked like, the tracks and traces, all of those are done here. Okay, if you should open a 3D view of this, this is your current PCB. These are pads. These are parts for the ESP32. You know how the ESP32 module looks like. You know that you can solder these here. So this is called a footprint. A footprint defines the physical layout of whatever device you are going to solder onto your board. All right. And all the symbols we've used in the symbol editor, we haven't specified their footprints. So when we are done, we would have to do that. So I'll just click close and this card changes. So when we still add a footprint, we wouldn't be able to connect this here. We can try it when we get there. We'll try it and see. So for now, I think that's no. You never want to have no pin connected error. Just put an X there if you are not connecting it. Is that alright?
Yeah, that's fine. Thank you.
All right, you're welcome. So if Aram is the only person who is asking a question, I'll continue. If you have a question, you can interrupt me. Okay. So the third, before we continue, let's do something here. As I said, you want things to make sense, so change this to UART. What did we change? We changed the name here. This is the value field. Value field. This is the reference field. References are usually automatically generated, and value fields, you can specify them. For the resistors and capacitors, we change the values to the value of the capacitor or the resistor that we are using there. For these ones like headers, what do we change them to? You can use the function, all right? So I want to show that this header is going to be for UART, so I change that to UART. Same over here, turbidity sensor. Just make it turbidity over here, ultrasonic. All right, and one more symbol that we are one more device, one more device. So okay. So this one is going to be tricky. I still wanted us to work on this because it's going to be tricky. But let's go through it together, all right? Okay. So you want to turn on or off a pump. Um, this is 5 volts. This requires 5 volts. This requires 12 volts. But let's look at the 5 volts. Let's say you are using an Arduino Uno, which can produce 5 volts at any of its pins. Okay. Um, can you just use it to power this water pump? And the answer is no, you can't. All right. The reason is that the pump requires higher current than the Arduino pin can deliver. The pins on the Arduinos can be used to turn on LEDs, check whether buttons have been pressed. You can think of them as signals because they output very little current. The signal will be used for something else, but to power an actual device, the pump requires power, like power in that sense. So to power an actual device, the digital pins on the Arduino will not be able to do that. And same is said for the ESP32. The pins on the ESP32 at best are for communication, sending signals, and then maybe somewhere in the middle you can use them to turn LEDs on. LEDs don't require much power. Okay, but for pump, it's a no-no. And even this one, which requires 12 volts, you can't even use the Arduino to power this. So how are we going to control this? How are we going to control this? And one device that you can use to control this is called a relay. A relay. So these are pictures of relays. They look different. There are varieties of them for different applications, but the common one we'll be using is something like. So what a relay simply does is that, let's look at this one right here. Now even this is not accurate. Let's look at this. I'm trying to find it. So I think we should use this. Yep. I think we should use this. So this is how a relay basically works. The relay has one side called the relay coil and the other side called the contacts. The relay coil, I think, is these two pins at the back Or is it? No, it's not. Sorry. It's the two pins at the back here. And then the contacts are the 1, 2, and 3 here. 1, 2, and 3 here. So here is how it works. The coil is an electromagnet. Okay. An electromagnet is a device that, when supplied current, produces a magnetic field. Okay. So the relay coil is going to be fed or driven by any of the digital pins on the ESP32 or on the Arduino. And then the contacts are the control pins. So take, for example, the 12-volt pump. Let's say you have a 12-volt power supply. So you're going to bring in a 12-volt power supply, all right? But now you want to control its turning on and off. One way you can control a 12-volt power supply to a pump is by you manually turning it on and off. But you want that control to be done by the microcontroller, right? So we are using something that, when it energizes this relay coil, the switch is going to be at one position. When the relay coil is de-energized, that is switched off, it moves back to a default position. So simply turning this on and off is going to toggle the switch position on and off. And this is not a simple switch. This is not a simple switch because at one state, the pole will be on the normally closed contact. So normally closed means that when this is not energized, it's always going to be in this position. Normally open means that when this is not energized, it's always going to be in this position. Meaning the pole would, if you buy the relay, the pole would always be connected to this. Okay, so the pole, which is this, will be connected to normally closed contacts. All right, so to use this as a switch, we are going to wire here and here to our pump, because when it is open, the pole is not connected to the normally open. It's normally opened. So now if we want the pole to switch to the normally open, we will have to energize it, right? And that is safer than using normally closed. Um, I hope it makes sense. For some of you, you've used a relay, you have learned about relays. For some of you, you might not have. But simply watch a YouTube video to understand how relays work. I think that'll be best. So at this point, you can just, if you are going to use the recording, you just pause here, open YouTube, find a short video describing how a relay works, and then come back. All right. So let's include a relay in our diagram. So I search relay, and I get a lot of options. I get so many options. Which one? Which one? Some of these are generic relays. Some of these are brand relays. Okay. You don't want to come to solid state relays. You know, solid state relays are something else. You just want to be in the relay section. And yeah, this is what we need. So I quite remember what I was looking for. Relay SPDT SANU RG series form C. The reason I know this is the footprint I need is that oh wow, I have to close this. Okay, so the reason I know I need this footprint is that I searched for our relay online at Oku Electronics. So I searched for an SPDT, which is single pole double through, single pole double through, single pole double through. That is, so this is a single pole double through because we have one pole, and the pole can be thrown in two directions, or to connect to two contacts. So single pole, double throw. You get it? So single pole, double throw, 5-volt relay. 5 volts is the voltage required to turn the relay on. The voltage required to turn the relay on. Let me. I don't know if we, okay, we wouldn't get some. Don't worry. So we'll use this Songo relay. From here, I searched for Songo relay dimensions. Songo relay dimensions, and this one looks like it's accurate. You can. So this is, you look here, this is SRD05 VDC. SRD05 VDC. So that's what is here. SRD05 VDC. You can open these two. So I'm gonna open these two. Put them side by side. So I'm just going to look at the data sheet. The data sheet is going to tell me the dimensions of the pins, and I would cross check to make sure that the footprint we have is accurate. Okay, this is the same thing we have here. So you guys, once again, this is why we need to read data sheets. So if you come here, yeah, so this is in a different language, but there's really no need to panic because you know what you're looking for. You're looking for numerical numbers. You're looking for numbers, sizes. Okay, so if you look here, you can see that there are 3 types: C type, A type, B type. The one we are going for is the C type, if you remember from the picture. SRD05VDC SL-C. For some of you, all of these letters and stuff don't make sense, but as you progress, it will make sense. I know this is C type because here ends with C, not an A or a B, a C. And when you come here, the C type is actually the type we are using. It has 5 pins. The rest are 4 pins. This has 5 pins. Okay, so what are we going to measure? We are going to measure the sizes of the pins. First, the diameters of the pins. So this is what they are saying. Okay. So over here, 2-0.5 and 1.1. It means that looking at the relay from this side, okay, so the middle pin, this middle pin, they said it's 1.1 in diameter. That is this one. Okay, so what you are going to do is that you are going to measure the diameter of this hole. Make sure it's 1.1 or higher. So you click on the ruler 2, which is at the side here. I recently experienced this where I was using my PC and the ruler 2 was not appearing anymore. So if it's not in the sidebar here, you can go to inspect measure 2. Okay, and when you come here and you are trying to measure diameter, it's kind of snapping to the edges. It's kind of snapping to the edges. So click here, click here. The hole is 1.3. Our pin is 1.1, and that's actually fine. You usually want your hole to be a little bit bigger than the pin, not too much, a little bit. So this is bigger by 0.2 mm, to allow easy slotting of the relay into the hole. Okay, and if I come here, I'm told that these 2 pins at the back, 2 of them -1, 2-1, it means that 2 pins are 1 mm. Over here, I knew it's 0.5 because they said sorry, I knew here is 1.1 because here is just 1.1. Their control, their control pins, right? They're really coil pins. And because those ones aren't carrying more current, they've made them smaller. And then the ones carrying current, sorry, let me pause and take this call. Okay, let's continue. So this is what I really mean. This is what is going on. The really coil pins, these two, one, two, are made smaller because they are not carrying much current. It's just being powered by a GPIO pin. It's not going to need much current, so they made them smaller. And then the ones that are actually carrying the high voltage, high current, those are bigger. All right. So that's how I'm able to intuitively know what they are measuring and what they are not measuring. All right. So for the small pins at the back, their size is 0.5. Okay, let's quickly check that so that we can move on. Small pins here, 0.5, and it's actually 1. I think 1 is okay. Perhaps there are some relays that use a larger size, so they are 0.1. And then the ones carrying current, 1.3, 1.3, 1.3. Okay, so this one has to be 1.1 and the other one has to be what? 1. So 1 and 1.1, but we have 1.3. That is okay. That is okay. So that's for the pin sizes. Now the separation between the holes. The separation between the holes, that is how far this is from this and this is from this. That is where we come here. That is where we come here. So 12 12 is the separation of this from this from this. Is the separation of this from this from this. So let's check them. For separation, you want as little deviation uh, as uh, different from the pin, the hole sizes, right? Deviation has to be at best like accurate. Okay, so I measured 12. What's the separation here? So if you want to measure the separation between this and this, you try and get the middle. So you see it's snapping to the middle of the pin and you measure to here. And we have 12 and a small deviation which is 0.5 mm. 0.5 mm is really small and I think that's acceptable. Same thing for this one. This is actually 12, like 12 on the spot, and this is 12.05. I think that's acceptable. Okay. Okay. And now the separation between here and here is 12.2. 12.2. So let's measure from here to here. 12.2 exactly. It should be the same for the top, I believe. Nope, for the top we have. Okay, I didn't measure it well because y is not 0. If you are measuring straight lines like from here to here, it's not straight because y is 0.5. If it's, let me measure the bottom one again. Make sure it snaps. Make sure it snaps to the middle. Y is 0.00. So the x you've measured is 12.2. So make sure this snaps in the middle and this snaps in the middle. Okay, and so it means that the footprint is a bit staggered. Don't worry about that. The point is that we have 12.25, and I think that is okay. I think that is okay. And lastly, from here to here, from here to here, the x value, which is from here to here, is 1.95, and the y value is 5.95. I'll bet you they'll tell us that x should be 2 and this should be 6. So let's check it. Okay, yeah, they've done that. So from here to here is 2. From here to here is 2. And then whereas from here to here, it's not stated, but intuitively, if from here to here is 12, halfway is 6. All right, so that's how we know that. That's how we cross-check footprints. See, the thing is that footprints are designed by people. People look at this data sheet and then they try and create these footprints. Those people can make mistakes. So for any footprint you are going to use, at best, you want to check and make sure that it's accurate. For the ESP32, because I've used it before, I know it's correct and I'm not going to cross-check it. For this relay, this is my first time using this footprint. I have not done a PCB for a relay, so I was checking that. And I think as engineers, you want to cross-check stuff, else you will be the one to pay for it. Okay. So now form C, back to our schematic. We are come to add a relay. And if you scroll down, SANU SRD form C, this is the same footprint. So let's add this. Let's put this here. Actually, so let's rotate this. And something like this should be okay. Okay. Did I close? Yeah. Don't close this. It's going to be very important. This is going to be very important. The pin labels is going to tell us how to connect the relay. So I'm going to take a picture with my phone so that I don't have to keep jumping. To have this open too. Okay. So you see, the thing is over here, the relay coil. I think I'll call this RC here and here. All right, where the 3 are, the N2. On the symbol, that is 5 and 2. 5 and 2 are the relay coils. On our schematic, 5 and 2. That is here. Okay, so I'm going to do a label. Well, I'm trying my best not to make it long, but well, the coil 1. Can make it RC1. I think that will make more sense. Our schematic is not too big, so they should be okay. RC1. RC2. Connect these up. And we would come back to it. We would come back to it. Now our pump, how are we going to connect it? How are we going to connect the pump? Whether this or this. So pumps just have 2 wires, positive, negative. If it's a 5-volt pump, red gets 5 volts, black goes to ground. For the bigger pump, I remember using this. This also has wires. If it doesn't have wires, you can just cut wires and then connect them there. So I'm going to use connectors for the pump. I'm going to use a 2-pin connector. I'll go with the socket because no, not 1 pin, 2-pin. Pin socket. Let's say here, quickly rename this to pump. Put a ground there. And we are going to need a symbol here. That is where the output from the relay is going to come. So as you remember from the data sheet, so if this is top down, or let's look at the images and see something. Okay, so from the image, this is better. From the image, this one is the normally closed, this one is the normally open. Now how are we going to translate that? Okay, let me look at what we have over here. So over here, the 3 pins are on this side. Okay, over here, listed the pin 4 is the normally closed because of this line. Pin 4 is the normally closed. Yeah, that's correct. So pin 4 is normally closed. We are going to use pin 3. And it's the same over here. This is connected. 1 is connected to 4. So pin 4 is normally closed. We will put do not connect here. Nothing goes here. Over here is going to come from our 12-volt supply. Sorry, wrong place. 12 volts. Going to get 12 volts from here. 12 volts. And then when our relay is energized, all right, when our relay is energized, this will flip to this, and then 3 should connect here. We can easily connect this like this, but no flags. Remember, flags. So pump power. I'm coming up with all of these names on the spot. We really want to use something that makes sense. Pump power. All right. And the one mistake I just realized I made. Here should actually be ground. Here should be ground. Because all you have to do is supply 5 volts here, and the other side should be ground. Alright. To energize the relay. I hope no one is confused. Let me pause once again, and if any question, we will take it. I'll also take a water break. Okay, so I think we can continue now. So to summarize the relay, it makes sense here. Simply supply 5 volts here. Simply supply 5 volts here to the coil, and the coil is going to energize. The coil will be energized, and this switch will toggle here. So this is just a control device helping us to supply 12 volts to the pump to turn it on and off. All right. Okay, now we are not done. We are not done. There is an extra component we have to add to the relay, and this is called a freewheeling diode. a freewheeling diode. Now, let me show you freewheeling. So really freewheeling, what does it? So it says that freewheeling diode is a relay circuit. A freewheeling diode in a relay circuit protects components from voltage spikes caused by the collapsing magnetic field when a relay coil is de-energized. Right, so simply what that means is that when you have energized your coil and then suddenly you turn off the 5 volts to it, at that point there's going to be an increased voltage at the terminals of the coil. It has to do with it being an inductor. The coil is an inductor. For those of you who have studied power electronics or something related to that, you know that you never short circuit an inductor because there's going to be dangerously high voltages at its terminals. So what we use is a freewheeling diode. And how do we connect it? Well, let's just look over here and see. Yep, so this is how a freewheeling diode is connected. You put a diode across the coil, but then the negative part is connected to the positive supply, because when this is positive, the diode is off, all power flows through here. When you turn this off, the relay wants to continue forcing current to flow through it in the direction it's flowing. So then when this goes off, this diode turns on and it acts as a short circuit path for the magnetic field to collapse through it. Else there's going to be a high voltage at the supply pins, and in our case it's the microcontroller, and you could damage your microcontroller. Okay, so a common diode uses the 1N4148, and I believe Oku has this. Fingers crossed, he should have this. 1N4148. Fingers crossed he has the 1N4148. And these are, this is what it looks like. Okay, there's something else I've come across. Let me quickly search. And we are told that we can use either this or this. I think I'll go with this. Let me quickly check the schematics, make sure it's around. And that's the 1N4148. Let's place it there, and So far, I think I've made an error, a very big error. Yeah. Apparently, the coil of a relay can't be driven by a digital pin. True. So we need a transistor. We need a transistor. We need a transistor, an NPN transistor. And the common one is 2N quadruple 2, or this. So 2N quadruple 2 is around. This is not around. How about this? And this 2 is around. Just checking what we can do and what we can't do. I really have to check this. L, SL. We're looking at 5 volts. 5 volts MA 71. So yep, this is cool. This is cool. Yeah, I was just checking some stuff out and I think we can continue. So the transistor I'm going to use is this one. I'm being tempted to use this for some reason. Getting, I'm really not getting the package type. Okay, I told you that it's TO92. Yeah, yeah, I know the past 5 minutes have been confusing. So this is the rundown. The rundown is that we cannot use a microcontroller pin directly to power the coil of the relay. We can't. What we have to do is that we have to rather use a MOSFET 2N2222. There's no 2222. This one is around. Let's go with this one. Let's go with the truth is that you can use either this one or the 2N22. So relay transistor and diode connection. There are a lot of them over here. So one that we are going to use, I think we can use this. Let's try and make sense of this. So as I was saying, the freewheeling diode connects across the relay. The negative of the diode being where you'd supply positive. So I'll supply positive here. Then I'm going to bring this one here. Let me send this down there. Is this here? So I'm going to hook this up like this. Hook this up like this. Freewheeling diode is complete. The transistor, this is how we have to hook it up. So most of them place 5 volts through the relay first, and then instead of the transistor being between VCC and relay, it's rather between ground and relay. That's how most of them have done it. The transistor is between ground and relay. So I'm going to move this here. I'm going to look for 5 volts. So I'm going to put 5 volts here. 5 volts is here. Now the transistor, how do we connect it? Let's try to make it like this. So this is how we connect the transistor. This is connected here. And then this is connected here. So what happens now? This comes here. And most of them have a resistor there. That is a current limiting resistor. So this is where we need the data sheet. We need the data sheet. Let's see if there's an application circuit. So there is no application circuit. So how are we going to know what resistor to put at the base? Okay, so from intuition, this is what I think. So we are going to supply 3.3 volts to the base of the transistor. All right, let's take a look at the schematics again. So this is what is happening. To energize our relay, 5 volts is supplied here. Current has to flow through the coil and then through the transistor to ground. That's a complete circuit. But this transistor is being controlled by this RC1. The RC. Let me now make it RC. Or let's make it coil. Okay. But then based on the data sheet of the transistor, I think there is a voltage and a current, maximum voltage and current allowable into the base of the transistor. That is my intuition. Let's check from the data sheet. Let's fish it out. So you don't have to read everything. What you have to look for is so collector emitter voltage. Max is 40 volts. We are allowing 5 volts, so we are within range. Collector emitter. Collector base voltage 60. That's the max. We are not exceeding this. Emitter base voltage 6 volts. We are using 3.3 volts. We are within. Collector current continuous. So I was checking the data sheet in a different language. The reason I was able to know was that I came here to MA. MA is the symbol for current, and we are using version L. Version L because this is an SL. I mean, I just knew it. Version L, and we are using 0.5, that is VDC, 5 volts. The current that the coil draws is 71.4 MA. 71.4 MA. And collector continuous current is 200, so we are well within our range. And this is the power dissipation. Power dissipation. Okay. Mm, okay. Okay. Let's, yeah. Truth is that I've never done a relay circuit on a PCB, so I have to check something with a transistor. So with a transistor, this is what we want to do. Um, Transistors have PN junctions in them, and to activate a PN junction, you need something like above 0.7 volts. Our ESP32 provides 3.3 volts, so that is well above um, 0.7 volts. But then the effective voltage is, you are using 3.3 minus 0.7. Effective voltage is 2.6 volts. Okay, so we are applying 2.6 volts and we want to control the current. we have to control the current into the base. I don't know whether there's a stated base current, maximum base current. On this graph, we have from 0.0012 to what's 10 MA. Base cutoff current is 50 MADC. I think that's the lowest current into the base that it will turn off. Base current. Okay, let me check something with Gemini. Let me check something with Gemini. Yeah, AI helps with these calculations. So what I'm getting here is that required base current to ensure the transistor turns on completely. The base needs a small amount of current. A good rule of thumb is to provide the base with about 1/10 to 1/20 of the collector current. So the collector current is what the relay is drawing, which was 70 something MA. Let's say it's 80 MA. Divided by 20, we have 4 MA. So 4 MA with 2.6 volts is 650 ohm. 650 ohm, but there is nothing like 650 ohm. So the next good value is 680 ohm. And of course, I want to verify that. So I come here and I'm going to look for 680 ohm. Hopefully it's there. And look at that. There is a 680 ohm resistor. So we are going to go with this 680 ohm resistor. Bring in a resistor. Need to delete this line. Let me delete this and bring another one. Okay. Connect this up and then bring this here. R 680R. I told you guys for kilo ohm, if it's 680 kilo ohm, 680 kilo ohm, it's 680K. But if it's just 680, you add R at the end. It's common practice to do that. And with that, we have that section finished. We have that section finished. So we have our UART, we have our turbidity, ultrasonic, and our pump section connected. We have stuff left to go. We have other things to do because run ERC, we have 6 warnings. We have 6 warnings. Let's tackle the easiest, and that is the non-connected terminals. Okay, the non-connected terminals. This is where I'm going to pull up this ESP32 room 32E pin out. All right. Module pin out. I'm going to go with last minute engineers. ESP32 pin out reference. So the pin out diagram is simply telling you the pins you have, what you can use them for. So for our ESP32, this is the pinout of the physical chip. The pinout of the physical chip. And so if you look at this, you see that pin 1 here is ground, pin 2 is 3 volts, pin 3 something is there. I think that's the enable. I'm not so sure. Here is ground. 35 is TX RX. Look at the diagram. Ground 3 volts EN, ground, and then T35 TX 34 RX. You get, so the pinout is accurate from what I'm seeing. So what do we want from the pinout? We want the pinout to give us pins we can use to connect our stuff. Our stuff are turbidity, the turbidity analog input, the uh, the echo, the trig of the ultrasonic sensors. All right. So this is what I'm going to do. Okay. So I'm going to use uh okay. There is one more thing to do. One more thing to do. This is the problem. This is the problem we have over here. So with our turbidity and ultrasonic sensors, these are 5 volts devices. Our ESP32 is a 3.3 volts device. If they are to give signal to the ESP32, we could get into trouble. So we have to find a way to reduce the the we have to find a way to reduce the voltage. Okay, so that is what I just searched up. How to level shift 5 volt to 3.3 volts. And I got this diagram. Use a 1K 2K resistive divider. We are engineers, so you know what a resistive divider is. Resistors that are going to divide the voltage. So when 5 volts it's applied over here, we are going to get the 3.3 volts equivalent. Okay. And for the ultrasonic sensor, we just have to do it for the echo pin. The echo pin receives the reflected signal. Okay, the trig pin is the trig pin. The ESP32 is sending signal from the ESP32 is sending signal to the ultrasonic sensor, and the echo pin, the ultrasonic is sending signal back to the ESP32. So if I'm sending 3.3 volts to a 5 volt device, I'm safe. The 3.3 volts would be registered as a logic 1. But if the 5 volt signal is device is sorry, if the 5 volt device is sending signal to the 3.3 volts device, that's an overshoot and we have to reduce it. Okay, so just on the echo pin. So how are we going to do this? Let's drag this back a bit. Bring this here. So I'm just going to employ 2 resistors. Let me place a branch here. I think I'll need two here, two here. I hope so. I hope it's just two there, two there. For the smaller sized ones. Okay. So we saw from the image, this one is 1K, this one is 2K, and you do your math. If you do your math, which I'm not going to do, you realize that applying 5 volts here is going to level shift it. So this is how it's going to be. The signal is coming from here. This is the 5 volt signal you saw from the image we looked at. 5 volts comes through 1K, through 2K, and we add a ground. So let's add a ground here. Connect this. And then we get our 3 volts from the middle of them. So now this goes to echo. And yeah, that's the resistive divider. Yeah. So I'll just duplicate this. Let me delete this and duplicate this to the turbidity. Someone's mic is unmuted. Please, if you are not speaking, please mute your mic so that there may be no distractions. Okay, and turbidity gets it from here, I believe. All right. Okay. Okay. So back to where we were. This can go now. I hope no one is confused. Please, if you are confused, I can go through it again. Um, but whilst no one is confused, let's look for a pin for the turbidity sensor. Now, the turbidity sensor is an analog device. It's going to give us a range of values, analog values, voltage levels. Okay, so we need a pin that supports analog signals, and those pins are called ADC pins. ADC is called analog to digital. ADC the full meaning is analog to digital converter, because what is happening is that you are converting analog signals to a digital format for the ESP32 to process it. Okay, so the analog pins over here, ADC, are the orange ones. You see, the thing is that in the ESP32 pins, a lot of the pins are multi-purpose, meaning that GPIO 36 can act as a GPIO where you just apply ones or zeros, or read ones or zeros, or you read analog values. Okay. Over here, 35 is a GPIO, but it can be used for serial communication. And then we have touch pins, we have SPI, we have pins dedicated for SPI. SPI is also a communication protocol like UART. Okay, so that is why we have multiple tags over here. So the ADC pins are the orange ones. So which one should we use? Which one should we use? So a piece of advice over here. The pin should be physically close to the headers. Here is what I mean. This is our PCB, all right? Let's say we want to find a pin to connect this to from the ESP32. Let's say to connect to, all right? And I would place this diode here. I want a pin physically close to here, and one pin is 24 or 23. Provided that the pin is a support, maybe if I'm looking for analog, I should look for the closest analog pin. If there are none here, I would have to move the diode to maybe this section and use a closer analog pin. All right. So it would all happen in the routing, but for now I'm just going to specify pins. When Lemon is taking with the routing, I think he'll be at liberty to change some of the pins in order to make routing easier. It depends. It depends. So for now, I'll just focus on routing, like just connecting something up to make our ERC errors go away. So I think I'm going to go with GPIO 35. GPIO 35. And that is this right here. So duplicate this. Remove your not connected pin and connect this up. Alright. And now I need GPIO pins for the trig and echo. I would go with 34 and with 33. 34, 33. Okay, so trig and echo. 34, 33. Echo are connected. And finally, I think I'll go with 32 for the coil. 32. Yeah, we can use that. So coil 32. Okay, let's server ERC reduction. Okay, ERC errors have reduced. What is left? We have to create 5 volts and 12 volts. I'm going to delete these two so that I remember to create 3 volts too. Now we have 4 errors. Else we think 3 volts is already there, but it's not. Okay, so this is what I'm thinking. This is what I'm thinking. That this system is going to be powered by a 12-volt adapter. 12-volt adapter. Let me show you what it is and where it is. This is a 12 volts 2 amps adapter. Some of you have seen that, most of you should have seen adapters like this. Okay, so this is going to be the supply of the system. We will bring in 12 volts because that is the highest voltage we need. And for the rest of the voltages, we are going to use voltage regulators to step them down. Okay, so how are we going to start? First, we are going to use a connector for the 12-volt adapter. And the kind of connector for this is a DC barrel jack. In fact, let me list all the devices we need here. DC barrel. Let it load, let it load. Here's the barrel jack. It's impossible to find the female. The female is not here. It's, but they had some. They are supposed to have some. They are supposed to have some. Let's check site number 2. I thought Oku would have everything, but he definitely doesn't have everything. This is what we are looking for. This is what we are looking for. DC barrel jack. So yeah, there's some out there. There's some out there. So we simply include the DC barrel jack over here. Let's shift more stuff. Shift this here. Shift this here. So that our power can be here. So barrel jack. We have barrel jack with mountain pin. Uh, so I think we are going to use this. Okay, if we look at the barrel jack, it has 3 pins. One of them is positive, the other 2 are for negative. So most of them say the top is the positive, the bottom 2 are the negative. Yeah, so the top is the positive, the bottom 2 are the negative. All right. So this is positive, 2 are negative. Okay, I'll put that here. Barrel jack is bringing in 12 volts. So where is our 12 volts? That is here. And then the other 2 are grounds. Okay, that's good for 12 volt barrel jack. So 12 volt supply. We have a 12 volt supply. Let's add a decoupling capacitor. Let's add a decoupling capacitor. I think 22U. I'm thinking 22U because we are powering a pump. Pump needs significant amount of supply. So let's go with this. Okay. So we will decouple over here. It's advisable to add another one at the pump. Sorry, at the where it's going to. So let's add a 1U capacitor. This is once again just for decoupling. Just for decoupling. Just for decoupling. Okay. Okay. 2 more things to go. A voltage regulator to give us 5 volts and a voltage regulator to give us 3.3 volts. Okay, let's get it done. Let's get it done. So we can close what we are not using. 5 volts regulator. 5 volts regulator. We have this. Let's see whether there are others. We have this, but this one is an SMD part. I don't know whether you guys want to challenge yourselves trying solder SMD parts, but if you don't, I think you should go with this kind, LM7805. Let's check whether it's in keycard. LM7805, and it's there. It's proudly there. Place this here. Let's look for 3.3 volts. Okay, the only one we get is this. So this one can give us up to 1 amps of current, and this 800 mA. And I think that's enough because the ESP32 itself at max power output, you're using 500 mA. That's when Wi-Fi is active and everything else is active. 800 mA is well above what we need. Let me copy this and see whether we would find this in keycard. And yep, we would find it. However, these ones are the SMD versions. They, these ones are the SMD versions. I'm just looking for the package. Okay, this is a TO220 package. Let's check for Mouser 2. Yep, this is a TO220. In keycard, let's see whether we have a TO220. So I'm just going to bring this in. Use the 3.3 version. I'll just bring this in and then we'll change the package attached to it. So we are told we are using 220. 220-3. So we have a number of them. We have a version where the regulators, you've bent them so they are lying down flat on the board, or they are standing straight. To save board space, you want to use the straight standing type. So we would use this for the regulator. Okay. So quickly connect things up. First off, let's go back to the data sheet. Typical application over here. So over here I have to check this before I continue. So for the 5-volt regulator, the input voltage is from 7 volt to 35 volts. Our input is 12 volt. We are well within range. That's one thing we should have checked earlier on. And for this one, from 4.75 to 15, 12 volts, we are well within range. You'd want to check input voltages because, for example, let's say you are supplying 24 volts. You can't use this regulator, else it will burn up or something like that. Okay, so in this circuit diagram, this is how you are circuit for increasing output voltage. Voltage regulator with reference. Let me check this one. Oh, okay. So the kind of circuits I'm given is this. with a TVS diode, we would eliminate this. We'll eliminate this because so it's the capacitors I want to know. The, the capacitor values that I want to know. So 100 NF, 10 UF. Is that what was given before? In is 10 UF, out is 100 NF. Is that you can use a mixture of them. 100 NF, 10 UF. I think I'll use 100 NF and 10 UF over here. I'll give you my reasons now. So the reason why I would use 100 NF at the input, you guys remember, as I said, 100 NF is for filtering. 100 NF is for filtering. You want to reduce the amount of noise as much as possible that is entering the voltage regulator. Okay, so that I can perform efficiently. That's why I'm going to use 100 NF at the regulator only. Okay, when we have this bulk decoupling capacitor at 12 volts, so we don't have to add a 10 UF here. All right. However, when we get our 5 volts, we should add it's 10 UF, right? Now, so just picture it from here. At 12 volts, there is a bulk decoupling. So now at 5 volts, there should be a bulk decoupling. Let's go for 10 UF, which is not here. So I'll just duplicate this and change this to 10U. Okay, 10U. And then where's my 5 volt symbol? 5 volts is right here. Okay. So just like that, we are done. We are done over here. For this one, LD. Oh, whoops. Wrong device. Wrong device. This guy should be here, rather. This one should be here, rather. Change this. No, delete this. Because the data sheet we're looking at was the LD1117. So we are rather to bring 3 volts here. So this here, I'll bring it back when I'm done. Now for this one, once again, connection circuit. The number of images suggests a 0.22 UF, which is also a filtering, and a 0.1 UF, which I think is also a filtering capacitor. Let's check the data sheet. Straight to applications. So typical application of a fixed output regulator is that the output will have 0.1 UF, input would have 0.33 UF. This time around, I'm going to go by what was given to me. Almost 5:30. Let's hurry up and finish at 5:30. There's no 0.33 UF capacitor. Let me try 330 and so I think a 0.22 would be okay. You just have to play with the values and make sure you get something that is around. So I think for this, I'll just go with a 0.1 UF because it's the closest. 0.2 to 0.1. They are quite close. So 0.1 UF it is. 0.1 UF it is. The data sheet says 0.1 here, 0.33 here, but we are using both 0.1 and 0.33. Connect those up. Actually, yeah, that's simpler. That's simpler and cleaner and easier. Okay. So you guys get what is going on. We started from the bottom upwards. We focused on our ESP32. We assumed that there was 3 volts somewhere there, and now we are now doing the actual power supply. So yeah, in PCB design where you see those complex stuff, just know that it's doable. You just break it down into smaller parts and then you just work on them. Let's run the ARC and see whether we have any errors. Okay, what is the error? So for 12 volts, we still have to connect a a, a power flag to it. I'll place it here and I'll delete the name. And then the same to is said over here for the ground. So I'm going to duplicate this and place it here. Run ERC. And that's it. We are done. We are done. This is the last step now to assign the footprints. And to do that, you come here to footprint assignment. Footprint assignments. Now, the yellow colored ones are the ones with no footprints. The white colored ones are those with footprints. Now, you want to verify those that already have footprints first. You want to verify them. So I clicked on view selected footprint and this is the one we are supposed to change. LD1117 according to the data sheet. is a TO220-3 package. TO220-3 package. So to assign a footprint, at the top here, footprint filters. You want to turn all of them off first. When all of them are active, this one uses symbol footprint filters. This one by pin count, this one by library. So I'll leave the pin count one on. Okay, I'll leave the pin count one on, and I'll search TO-220. TO-220, and I get 6 options. I get 6 options. So the one we're supposed to use was the vertical, but there are 2 verticals. So let's look at how they look like. This one is this, and then this one is this. Question is, what is the difference? Question is, what is the difference? I honestly don't know. TO2 220 versus TO220F. Okay, okay, okay. So for now, for application, we don't really need to worry about that. I would go with this one. So you double click number 3 to assign it here. Let me check the other ones. This one is correct. The SB32 I know is correct. This one, yes, is correct. If you want to use the ruler tool, 1.27, 1.27 pitch. When we checked our data sheet, so 1.27, yeah, 1.27, so I know that's correct. Let's continue with the rest. Resistors, okay, resistors. Which size are we going to use? Which sizes of resistors are we going to use? Capacitors to the same. Now the resistor, no, Oku electronics. So he has a bunch of resistors. They look almost the same, a lot of them. Unfortunately, he has not given us the guy whom I know has not stated the sizes of the resistors on the page, so it's going to be hard to use it for PCB design. But here is a fair bet I think you can do. There is this kind of resistor footprint that saves space on your PCB, and this is it. So let me clear here. Filter by filter by numbers. Okay. I'm not using resistor SMD. I'm looking for resistor THT. THT vertical. This is how they look like. Open the 3D model. This is how the resistor is mounted. Yeah, it's mounted like this. This saves a lot of space as compared to something like this horizontal one. Yeah, this one is the danger with this is that we don't know the length of the resistor. We don't know the length of the resistor. So if we use any length and the one that comes is longer, we are going to find a hard fit in it here. If we use the longer footprint and the one that comes is shorter, fine, it would enter. But it's 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 uh, it's a gamble unless you've bought the resistors and you measure the length. So honestly, I think we should go with the vertical sizes. We should go with the vertical sizes. So this one like this is a very big resistor. Nah, I wouldn't cut it. I think a safe one is this. L6.3 D 2.5 and pitch 2.54. This is a safe value I'm willing to gamble on. So for our resistors, for all of them, I'm going to select this. Okay. Jumper open. The open jumpers, they are just header connectors. Just header connectors. The headers are, let's use the side rather. So come to header, pin header 2.54. Connector pin header 2.54. Remember 2.54 pitches. 2.54 pitch. All right. So for the UART, we are here, we are here. Now it's going to give us these. Let's take a look at them. This one is a header lying down. So you rather do it's inserted sideways. We don't want this, it wouldn't save space. This one is what we want to go for because the other two are SMD versions. The other two are SMD versions. You look at it, it's soldered on top, not soldered through it. The one we want to use is this. It's soldered through the board. So this is what we want to use. Okay. So it has already filtered it. For the UART, it's a 4-pin connector, right? So we select this. Ultrasonic tool is a 4-pin connector. Select. Stability is a 3-pin connector. It has changed. So select. Pump is 2-pin and it has changed. So select. For the capacitors, that one would be last. That's the hardest. For this, we are going to go with this. Let's click this off. And I think this is the one we want to use. Yep, this is the one we want to use. So the jumpers, this barrel jack. Barrel jack. Oof. I think this one looks good. What do you know? This one looks good. Go with this. The barrel jacks have a standard dimensions. There aren't different kinds of barrel jacks and different. At least that's I think so. Maybe it's a company that want to make their own barrel jacks for their own devices, but the standard is that there is a size that everyone should use, right? So now down to the capacitors. Down to the capacitors. So for the 100 NFs, we said that we are going to use ceramic types, right? We check Oku Electronics website and for 100 NF, right? This is it. 100 NF. What is the size? Okay, we are given a size. Luckily, We are given a size. I wonder if I skip the sizes for the rest. No, we are not given any value. We are not given any value. Not given any value for the resistors, so I didn't skip it. But this one we are given a value, size 5 mm diameter. Okay, let's clear this. Use this. So we want to look for capacitor THT. And I know which one we have to look for. It's C disc, the ones with discs in them, because you look at them, this is how they look like. Yeah, it looks like a disc, that's why it's named like that. So we want a D of 5. We have a D of 5, but then width 2.5, width 2.5, pitch 2.5, pitch 5 mm. Wow, I've gotten a notification that the call is ending in 2 minutes. So let's be fast. Let's be fast. Okay, you guys know what? Um, the recording will continue, and then you can just watch the ending of the recording on YouTube to know the footprints I've selected for the capacitors. All right, but up to this point, I hope you all get it. Okay, for the routing, we will continue next week. Not with me, with Lemuel. Okay, so we have done up to 5:40, and I think we can close now. I would continue with the recording and I would send that to you. Just fast forward to the ending and see the values that I've chosen for my footprints. Okay, so I'm ending the call now, and I'll see you guys when I see you. I wouldn't be meeting you next week. Have a great evening. Okay, and I'll continue on with the recording. So on the Oku Electronics website, capacitance is 100 NF, size is 5 mm, size is 5 mm, diameter size, and we have two 5 mm diameters. This one is here, and this one. And I think I see the difference. With the other one where the pitch was smaller, it's because the legs were somewhere here, right under it. But this one, the legs are outside, like shifted outside, way outside. So what do we see here? What do we see over here? What do the pictures look like? Are the legs under or outside? I think they're under. They look like they're under. Or are they outside? Let me take a look at the footprint again. Wow, this is very tricky. This is very tricky. If we use a wide one, if we use a wider one, we can easily pull the leg. But if we use a smaller hole and the capacitor ends up being the wide type, we have to squeeze it in, and that's going to be hard. So I think we should go with the wide one. I think we should go with the wide one. That would be this diameter of 5, pitch of 5 mm. Same for 100 NF. Yeah. Okay, I think they are all the same. or the 100 NFs. Okay, moving on. Let's look for the common one now as 1U. 1U, 1U. 470. This is 1U. Okay, I hope we have a size. I hope we have a size. We don't have a size. We don't have a size. So this is going to be hard, but this is what I'll do. I have some capacitors there. I'll get a 1UF1 and quickly measure it and use the values I get. Okay, so I am back and I found one, a 1UF capacitor. Okay, so here is it. 1UF, 63 volts. I wonder if that is what is actually there. 1UF, we have 50 volts here, but they look the same. Hopefully, I think they are the same. Okay, so this is what we are going to do. That's how we are going to do it. One important tool for engineers is the vernier calipers. It helps measure distances. So something like this. We want to measure the pitch of the two legs. Okay, so I'm going to use the outer parts of the calipers to measure the pitch. And if you observe, we are getting 2 point something. I think it looks like 2.54 because 2.54 is quite a common value. See, it's not exactly on the 2. Not exactly on the 2. It's a little bit after the 2. So we'll look for something a little bit above 2. Okay. The next you want to measure is the diameter of the casing, the capacitor casing. And when I put the, let's measure the bottom side rather. So I get 0.5, something 0.5. So pitch 2.5 for diameter 0.5. Let's look for that in keycard. So capacitor THT. Let me look at this. What is the CP about? Okay, the CP is a triple pin type. Axial type is okay. Axial type is a different type. We are not using this. We are using radial type. We are using radial type. This is what we are using. So remember, pitch was 2.5. We have pitch 2.5, 2. Let's look for the diameter first. Diameter was 5 mm. So 5 mm we have for 2 and we have for 2.5. What should we go for? Should we go for 2 or 2.5? Let me take a look at their models and see. Honestly, I would go for the 2.5 because if it comes in as a 2, we can easily stretch the legs outwards. But if we do a 2 and we get a 2.5, it's going to be difficult pushing the leg inwards. Okay, so let's go with a 2.5, 5 mm pitch 2.5. Okay, let me measure the legs one last time and see what exactly we are getting. Are we getting a 2 or a 2.5? Starting to look more like a 2. It's Patterns look more like a 2. But I stick with my reasoning. I'll go with a 2.5. So 1U, 5mm, 2.5. 5mm, 2.5, 2.5. And now let's find the 10U and the 22U. Those ones are going to be hard to find lying around. So this is the 22U. 22U. 10U. The truth is that they all look the same. They very much look the same. They very much look the same. So for those two, I'm going to select what I selected. Okay. And we are done. You click apply save schematic or OK to close it. Run this ARC once again. We have no errors. Control save. Open your PCB. Remove what we brought at first and then click update. Over here we have no errors because we've assigned all the footprint close. And our stuff are ready for routing. You can see some RustNet connections, which are these blue lines. If I should turn them all off, they are gone. RustNets are gone. They are back. So routing can now start. Well, thank you.